February 16, 1943. The small turning tool vibrated subtly in the grasp of Oberingenieur Klaus Hermann as he commenced the unsealing of the metallic container enclosing the captured American radio apparatus. Surrounding him, 5 of Germany's preeminent radio engineers leaned intently forward, keen to scrutinize the apparatus that had fortuitously come into their possession during the recent engagement at Kasserine Pass. For 3 years, they had been apprised from Berlin that American technological advancements were inferior, mere mass-produced detritus fabricated by a nation of merchants and assembly line laborers. The Radio Intelligence Service had reported that American forces relied upon antiquated materiel, primitive schematics, and inadequately trained personnel. Yet, a discrepancy persisted. Allied formations maintained unbroken communication across improbable expanses. Their naval armadas never relinquished contact. Their ground elements executed maneuvers with a precision that suggested a far more sophisticated system than the rudimentary radios depicted in German propaganda. The container yielded its contents to reveal an SCR-508 radio set, recovered intact from an American M4 Sherman tank that had been rendered inoperable within the Tunisian mountain range. What Hermann and his cadre would uncover in the ensuing 72 hours would irrevocably shatter every assumption held by German military planners concerning American industrial capability, technological sophistication, and the trajectory of the conflict. The mathematical principles governing radio communication were poised to unveil a truth more devastating than any military setback. The systematic appraisal of American equipment would expose not merely a technological deficit, but an industrial disparity so profound that Germany's eventual defeat was, in essence, already presaged in the resonant frequencies of its crystal oscillators, its automated circuitry, and its mass production methodologies, which the Reich could never hope to emulate. The acquisition had originated on February 14, 1943, within the confines of the Kasserine Pass. Forces under the command of General Erwin RML, engaged in a desperate counteroffensive against Green American troops, had secured a tactical triumph, repelling the United States Second Corps by 50 miles and destroying in excess of 100 American armored vehicles. Amidst the wreckage, German technical intelligence units moved with haste, seeking weaponry, documentation, and materiel that might illuminate Allied operational capacities. Headman Friedrich Huber, commanding a signals intelligence detachment affiliated with the 21st Panzer Division, held standing directives to secure any American radio equipment in an undamaged state. In a crater situated to the east of the pass, his unit discovered an abandoned Sherman tank, its turret dislodged by a German 88mm cannon, but its radio compartment miraculously preserved. Within, WWII located not one, but 2 complete radio systems, the SCR-508, engineered for intertank communication, and an SCR-510 receiver. Both were found complete with their frequency crystals, cabling, and even the technical manual, still affixed to their mounting brackets. Huber immediately mandated the transport of the equipment to the nearest German technical facility, cognizant of the invaluable intelligence this discovery might yield regarding American communication prowess. The radios arrived at Technical Testing Station 12 on February 16th. This installation, concealed within a subterranean complex beneath Tunis, housed Germany's most accomplished radio engineers, individuals instrumental in the design of the Wehrmacht's own communication infrastructure. Oberingenieur Klaus Hermann, formerly the chief designer at Telefunken, spearheaded the examination team. Accompanying him were specialists in frequency generation, circuit architecture, manufacturing techniques, and signals intelligence. Their initial phase involved an external examination. The American radios were encased in heavy-gauge steel housings, coated in an olive drab finish, with rubber seals protecting every seam and connection point. Hermann noted in his preliminary report that the construction quality surpassed anything he had previously encountered in German military equipment. The casings were engineered to withstand moisture, dust, impact, and extreme temperatures that would render most German radios inoperative. However, it was upon opening these casings that the first significant shock occurred. Internally, everything was standardized, modular, and optimized for mass production. Each component adhered precisely to specifications detailed in the accompanying technical manuals. There were no manual calibrations, no technician markings indicating individual adjustments, and no variations that would necessitate skilled assembly. This was materiel designed for fabrication in the millions by semi-skilled workers within factories that could be replicated across an entire continent. Lieutenant Hans Schreiber, a specialist in frequency regulation, inspected the crystal units responsible for the radio's operational frequencies. He had anticipated discovering simple, low-cost crystals, perhaps even repurposed civilian components. Instead, he encountered precision quartz crystal oscillators, each meticulously ground to tolerances measured in parts per million, hermetically sealed within metallic enclosures, bearing specifications that would have demanded weeks of laboratory work in Germany. The SCR 508 incorporated 10 crystal-controlled channels. Each crystal was individually packaged, interchangeable, and labeled with its exact frequency specification. Schreiber counted the crystals twice, struggling to reconcile what he was witnessing. In Germany, crystal-controlled radios were exclusively allocated to high-command units and aircraft, where the considerable expense and scarcity of precision crystals could be justified. Here, within a standard American tank radio, 10 crystals were installed with the apparent casualness of electric light bulbs. He carefully extracted one crystal and examined it under magnification. The quartz was flawless, the electrodes perfectly aligned, and the frequency marked with absolute precision. This solitary crystal would have incurred a cost exceeding that of the entire German FUG-5 radio set in terms of both materials and labor. Yet, the Americans were incorporating 10 such units into every tank radio, and they had already manufactured thousands of Sherman tanks. The team's preliminary assessment revealed further disquieting facts. The radio operated utilizing frequency modulation, FM, rather than the amplitude modulation, AM, employed by German radios. FM was theoretically superior, offering static-free communication and enhanced resistance to interference, but it mandated significantly more intricate circuitry and exacting frequency control. German engineers had contemplated FM for military applications, but had deemed it too costly and complex for field deployment. Nevertheless, here was an FM radio, mass-produced, installed in a tank operated by junior American soldiers. The circuit board displayed automatic frequency control, AFC circuits, that maintained the radio's frequency lock without continuous manual adjustment. German radios required operators to constantly fine-tune their receivers to compensate for temperature fluctuations, component degradation, and power supply variations. American radios, it seemed, tuned themselves. Oberingenieur Hermann commenced drafting his initial report to the Wehrmacht High Command in Berlin. The words flowed with difficulty, each sentence contradicting years of official pronouncements and intelligence evaluations. He conveyed that the captured American radio exemplified a level of industrial sophistication that Germany could not possibly match. The components were manufactured with a precision demanding specialized factories, skilled laborers, and quality control systems that simply did not exist within the Reich. More alarmingly, the radio was unequivocally not a prototype or a limited production model. Every facet of its design screamed of mass manufacturing. The Americans were producing these radios in the thousands. Over the subsequent 3 days, the team meticulously tested every function of the captured radios. They connected the equipment to power sources, antenna arrays, and test instruments that filled the subterranean laboratory. With each test, their burgeoning sense of apprehension intensified. The SCR-508's transmitter generated 25 watts of a clean FM signal across any of its 10 selectable channels. The mechanism for channel selection was elegant, dependable, and required no technical expertise to operate. A tank commander simply rotated a dial to choose a preset crystal, and the radio automatically switched frequencies, recalibrated its circuits, and maintained impeccable transmission quality. In German radios, changing frequencies necessitated a trained operator manually adjusting multiple controls, substituting coils, and dedicating several minutes to retuning the equipment. Range tests yielded even more distressing results. Employing a captured American WWII antenna, the team established contact with a monitoring station 20 kilometers distant. The FM signal was received with absolute clarity, devoid of the static, fading, and interference that plagued German AM communications. Even when deliberate electrical interference was introduced from a simulated tank engine, the FM receiver's limiter circuits effectively eradicated the noise, delivering audio quality that German operators could only dream of. Lieutenant Schreiber concentrated his investigation on the crystal oscillator circuits. He meticulously traced every component, measured every voltage, and documented the design with exacting detail. What he discovered confirmed his gravest concerns. The crystal control system was not merely sophisticated, it was beyond the capabilities of German manufacturing to replicate. Each crystal oscillator required a precisely cut quartz plate, ground to specific dimensions measured in thousandths of a millimeter. The crystals were then housed in evacuated or gas-filled enclosures, with electrode spacing controlled to tolerances that German factories could not achieve in mass production. Temperature compensation circuits maintained frequency stability across operating temperatures ranging from -40 to +60 degrees Celsius. Schreiber calculated that producing a single crystal to American specifications would necessitate approximately 40 hours of skilled technician time in German laboratories. The Americans had integrated 10 such crystals into a single tank radio. With thousands of Sherman tanks already in production and similar radios equipping American jeeps, trucks, and command vehicles, the Americans were producing millions of precision crystals annually. He posed the pertinent question in his report: where were the Americans sourcing sufficient skilled technicians to manufacture millions of precision radio crystals? The answer, when it subsequently emerged from intelligence channels, proved even more startling. The Americans were not relying on highly skilled technicians. They had industrialized the entire process. New factories in cities bearing names such as Chicago, Newark, and Fort Wayne employed thousands of semi-skilled workers, predominantly women, operating specialized grinding machinery that produced crystals automatically. Precision measurements were conducted by optical comparators and frequency counters, not by skilled technicians. Quality control was statistical, with random samples subjected to testing rather than individual inspection. The Americans had successfully transformed a laboratory art into an industrial process. The examination of the radio's receiver section revealed further advanced technology. The super-heterodyne circuit design bore similarities to German receivers, but the components themselves were superior by every measurable metric. Vacuum tubes were manufactured to tighter tolerances with characteristics precisely matched to the circuit requirements. Capacitors and resistors exhibited stability ratings that German components could not achieve. The entire receiver was designed for alignment by semi-skilled technicians utilizing rudimentary test equipment, rather than requiring radio engineers with years of specialized training. Most notably was the modular construction. Every major subsystem, the transmitter, receiver, power supply, and control unit, was a distinct, replaceable module. A tank crew could extricate a malfunctioning unit and install a replacement within minutes, without the need for tools or technical expertise. Damaged modules would be returned to depot facilities for repair or disposal. This approach necessitated a vast industrial capacity for producing spare modules, but it ensured that American tanks maintained communication capabilities under conditions that would render German vehicles radio silent for days while technicians undertook field repairs. The team examined the technical manuals accompanying the radios. These documents, printed on high-quality paper with clear diagrams and simple instructions, presupposed operators with minimal technical aptitude. Operating procedures were reduced to numbered steps. Troubleshooting guides employed decision trees that any soldier could follow. Maintenance instructions specified precise replacement intervals for components, rather than relying on operator judgment. Herman recognized that these manuals revealed as much about the American industrial philosophy as the radios themselves. The Americans had acknowledged that frontline soldiers were not specialized technicians. Rather than endeavoring to train every radio operator in the intricacies of electronics, they had engineered equipment that any reasonably intelligent soldier could operate and maintain through straightforward procedures. This necessitated more sophisticated apparatus, but resolved the fundamental military challenge of preserving communication integrity under combat conditions. German radios, conversely, demanded proficient operators well-versed in radio theory, capable of performing field repairs and possessing the technical acumen to keep temperamental equipment functioning. These operators required months of training and years of experience, representing irreplaceable assets, and when they were incapacitated or killed, their equipment frequently became inoperable for their successors. By the conclusion of the third day, the examination team had meticulously documented every circuit, measured every component, and tested every function of the captured American radios. Their report to the Wehrmacht High Command extended to over 200 pages of technical analysis, substantiated by photographic evidence, schematic diagrams, and component specifications. The conclusions drawn were devastating. The Americans possessed radio technology that was, in key areas, 5 to 10 years in advance of German equipment. Frequency modulation, crystal control, automatic frequency circuits, and modular construction represented fundamental advantages that superior tactics or operator skill could not surmount. More critically, American radio equipment had been conceived from its inception for mass production. Every element of its design reflected an industrial ethos that Germany simply did not possess. Herman's report estimated that Germany would require the construction of 30 new specialized factories, the training of 50,000 additional workers, and an investment of resources equivalent to the entire annual Luftwaffe budget to parallel American radio production capabilities. Even then, Germany lacked the requisite raw materials, particularly high-quality quartz crystals and certain rare elements essential for precision components. The conclusion was inescapable. American industrial capacity had rendered technological superiority militarily decisive. The report reached Berlin on February 25, 1943. It was classified as most secret and distributed to only a select few senior officers within the Wehrmacht High Command and the Reich Ministry of Armaments. The response was an unnerving silence. No new factories were authorized. No emergency programs were initiated. The implications were far too calamitous to be readily acknowledged. Yet, the endeavors of Technical Testing Station 12 were merely commencing. In the ensuing months, additional American equipment fell into German hands. Each acquisition provided further corroboration of American technical and industrial preeminence. An SCR-300 radio, the celebrated portable walkie-talkie, unveiled FM technology miniaturized into a portable unit weighing a mere 18 pounds, yet delivering reliable communication up to 5 kilometers. German portable radios offering comparable range weighed over 40 pounds and necessitated external battery packs that added an additional 20 pounds. and SCR-299, captured in Sicily in July of 1943, astounded the examination team. This represented a mobile long-range communication station integrated into a truck, complete with an onboard power generator. The transmitter produced 350 watts of power across a frequency spectrum from 2 to 18 megahertz, featuring crystal-controlled stability and the capacity to change frequencies within minutes rather than hours. The SCR-299's associated receiver employed a helichrydine design with 15 vacuum tubes, multiple conversion stages, and a crystal filter for enhanced selectivity. German long-range communication equipment of comparable capability existed, but solely in fixed installations, demanding building-sized antenna arrays and dedicated power plants. The Americans had encapsulated equivalent functionality within a vehicle that could be transported anywhere and deployed within an hour. Each examination yielded the same recurring pattern. American equipment was designed for operation by minimally trained personnel, mass production by semi-skilled laborers, and maintenance through adherence to simple procedures. German equipment necessitated skilled operators, manual assembly by trained technicians, and field repairs undertaken by electronics experts. One philosophy scaled to millions of units and global deployment, the other did not. The technical intelligence reports originating from Tunisia, Sicily, and subsequently Italy documented not merely individual radio sets, but an entire philosophy of communication. American forces maintained unbroken contact, from squad level up to theater command, through multiple tiers of radio networks. Platoons were equipped with SCR-536 handy-talkies. Companies utilized SCR-300 backpack radios. Battalions deployed vehicle-mounted SCR-508 and SCR-608 sets. Regiments were outfitted with SCR-193 and SCR-299 long-range equipment. Each level possessed the capability to communicate with the levels above and below, thus establishing a web of connectivity that German forces could not replicate. More critically, all American radios utilized compatible frequency systems and interoperable equipment. A forward observer equipped with an SCR-300 could contact an artillery battalion 20 kilometers distant, utilizing an SCR-608 because both employed FM on compatible frequencies with crystal-controlled stability. German forces, in contrast, operated a multitude of incompatible radio systems, each requiring distinct frequencies, different modulation types, and disparate operating procedures. By the summer of 1943, German signals intelligence had cataloged over 50 distinct American military radio types, ranging from handheld transceivers to airborne command sets. Production estimates derived from captured serial numbers and intelligence reports indicated that American factories were manufacturing in excess of 100,000 military radio sets monthly. German production, encompassing all services and types, reached approximately 15,000 units per month at its peak capacity. The examination teams commenced analysis of captured American manufacturing documentation. Technical orders, parts lists, and maintenance manuals illuminated the infrastructure underpinning American equipment. Components were standardized across numerous radio types. Vacuum tubes utilized common base configurations. Crystals adhered to standard holder designs. Even screws, nuts, and bolts conformed to unified thread standards, enabling interchangeability. This standardization meant that American factories could readily shift production between different radio types without retooling. A plant producing SCR-508 transmitters could transition to SCR-608 units by modifying only a few fixtures and component types. Parts from one radio type could frequently be salvaged to repair others. The entire system was engineered for flexibility and scalability. German manufacturing, conversely, employed custom components for each equipment type. The FUG-5 tank radio shared virtually no components with the FUG-10 aircraft radio. Despite possessing similar electrical functionalities, each type necessitated dedicated production lines, unique testing apparatus, and specialized spare parts inventories. Altering production priorities required months of retooling and retraining. Oberingenieur Hermann was transferred to a larger technical intelligence facility in northern Italy by the autumn of 1943. He increasingly dedicated his efforts to analyzing American manufacturing methodologies rather than solely equipment design. His reports to Berlin evolved from technical assessments of radio circuits to strategic warnings concerning industrial capacity. He documented the explosive growth of the American electronics industry. Companies bearing names like Galvin Manufacturing, later known as Motorola, had transformed from modest radio manufacturers into formidable military contractors. A prominent manufacturer of amateur radio apparatus was producing advanced military receivers in volumes that dwarfed Germany's entire radio output. Western Electric, the industrial division of the Bell telephone system, managed manufacturing facilities employing tens of thousands of personnel, creating crystals, vacuum tubes, and complete radio units. These organizations had not previously been significant contributors to military supply prior to the year 1941. The United States had established a comprehensive military electronics sector in under 2 years by repurposing civilian factories, training new personnel, and implementing mass production methodologies perfected in the automotive and consumer goods industries. Detroit's automotive engineers had devised radio production lines that operated with the same efficiency as vehicle assembly plants. The German radio manufacturing sector, centered in Berlin, Munich, and Hamburg, remained structured as it had been in the 1920s. Smaller enterprises produced specialized equipment utilizing skilled artisans. Production figures were quantified in hundreds per month, not thousands per week. Quality was upheld through individual examination and manual adjustments, rather than statistical process oversight. Automated testing. Hermann's assessment, submitted in December of 1943 to the Reich Ministry of Armaments, was titled The American Radio Industry, an assessment of industrial capacity and strategic implications. It detailed American electronics production with devastating thoroughness. The industrial output of the United States on an annual basis was what it would take Germany 20 years to manufacture. The disparity extended beyond mere technology. It encompassed industrial organization and philosophical approaches. The report calculated that American factories could produce sufficient military radios to equip 1,000 divisions, even though the Americans only deployed approximately 90 divisions. This surplus capacity meant that American forces possessed an unlimited supply of replacement equipment. Damaged radios were not subjected to field repairs, they were simply replaced. Outdated models were retired and forwarded to training units. Newer, superior designs were consistently introduced, not as experimental prototypes, but as mass-produced hardware distributed across all operational theaters. Meanwhile, German forces carefully conserved every radio. Field technicians undertook repairs under active combat conditions, salvaging components from damaged units to keep others functional. Replacement equipment arrived sporadically, if at all. Newer designs remained in limited production because retooling would necessitate a reduction in the output of existing models. The Wehrmacht operated radios designed in the early 1930s alongside more recent equipment, creating significant maintenance challenges and training complications. The situation regarding crystal supply was particularly dire. By the end of 1943, German logistics officers estimated a requirement for 5 million precision crystals for current radio equipment and planned enhancements. Domestic manufacturing capacity stood at approximately 200,000 crystals annually. Even if Germany allocated immense resources to augmenting crystal production, It would take over a decade to manufacture 5 million units. According to intelligence estimates, the Americans were producing 30 million crystals per year. They had resolved the quartz supply issue by identifying deposits in Brazil, establishing mining operations in Arkansas, and even pursuing experimental synthetic crystal growth. American crystals were not only plentiful, but also superior in quality, achieving frequency stabilities that German laboratories could scarcely measure, let alone replicate. The examination of captured American testing apparatus revealed another facet of the industrial chasm. American radio factories employed automated test units that measured frequency, power output, modulation quality, and sensitivity in mere seconds. These testers were themselves sophisticated electronic instruments, manufactured in sufficient quantities to permit dedicated test equipment at every assembly line station. German factories utilized manual testing procedures that demanded skilled technicians and several minutes per unit. One captured test unit, a signal generator from the Measurements Corporation, became a highly valued asset at the technical testing facility. This single instrument, standard issue in American factories, could generate precisely calibrated signals across the entire radio frequency spectrum. Its manufacturing cost was approximately $300. The comparable German equipment necessitated a laboratory filled with separate oscillators, attenuators, and frequency meters, costing thousands of Reichmarks and requiring constant recalibration by engineers. By early 1944, the message conveyed by technical intelligence was stark and alarming. American communication superiority was absolute, irreversible, and progressively increasing. Each month, American factories manufactured more radios than Germany possessed in its entire military inventory. Every captured specimen exhibited incremental enhancements, design refinements, and manufacturing sophistication that Germany could not match. The introduction of American radar systems in late 1943 and early 1944 amplified this message with even greater impact. Radar represented radio technology pushed to its ultimate limits, employing microwave frequencies, pulse techniques, and advanced signal processing. The Americans were mass-producing radar units for ships, aircraft, and ground installations with the same industrial efficiency they applied to voice radios. A captured SCR-584 fire control radar, examined in March of 1944, demonstrated technical capabilities that German radar scientists had only theorized about. The unit operated at the extremely high frequency of 3,000 MHz, utilized a precision tracking mount with automatic following circuits, and achieved accuracy that enabled anti-aircraft batteries to destroy enemy aircraft with devastating effectiveness. The SCR-584 weighed over 10,000 pounds and required a dedicated vehicle for transport. Yet, American factories were producing them by the hundreds. German radar development had focused on long-wave systems operating below 1,000 MHz because German industry lacked the capacity to manufacture the specialized vacuum tubes required for higher frequencies. The magnetron tubes employed in American microwave radar demanded precision machining, rare materials, and manufacturing techniques that Germany did not possess. Even when German scientists designed microwave radar systems on paper, they could not be constructed because the necessary components simply did not exist within German industry. The systematic examination of captured American equipment continued as Allied forces advanced up the Italian peninsula and prepared for the invasion of France. Each new discovery added to the overwhelming evidence documenting American technical supremacy. Improved radios appeared regularly. The SCR-694, introduced in mid-1944, provided frequency-modulated tank communication with enhanced range and dependability. The SCR-619 aircraft radio offered hundreds of crystal-controlled channels and near-instantaneous frequency switching. Most significantly, the reliability of American equipment saw continuous improvement. Early production SCR-300 radios occasionally experienced issues with moisture intrusion and battery contacts. Captured units from late 1944 displayed redesigned casings, improved seals, and modified circuits that eliminated these problems. The Americans were not merely constructing equipment, they were consistently refining it based on field experience and integrating lessons learned into ongoing production. Conversely, German equipment often deteriorated in quality. As the war progressed, material shortages compelled the substitution of inferior components. Skilled laborers were drafted into combat units, replaced by less experienced personnel. Quality control suffered as factories prioritized quantity over dependability. Radios that should have functioned for years began failing after months of service. By the time of the Normandy invasion in June of 1944, German technical intelligence had comprehensively documented the absolute superiority of American communications. Allied forces landing in France carried more radios than the entire German army possessed. Every Allied company maintained radio contact with battalion headquarters. Every Allied battalion could communicate with division command. Artillery forward observers directed fire from distances of dozens of kilometers with flawless accuracy because their radios never lost contact. German commanders attempting to coordinate defenses found their communications disintegrating under Allied jamming, artillery bombardments, and the sheer chaos of battle. Radios that performed flawlessly on test ranges faltered in combat. Crystal oscillators drifted off frequency in the Norman summer heat, rendering inter-unit communication impossible. Battery-powered units drained rapidly due to the unavailability of replacement batteries. The communication network that German doctrine assumed would exist simply ceased to function under combat duress. The technical reports flowing back to Berlin grew increasingly desperate in tone. Oberingenieur Hermann, then assigned to Armament Operations Staff, wrote in August of 1944 that Germany had already lost the electronic war. Allied jamming equipment, direction-finding systems, and signal intelligence capabilities allowed the Allies to pinpoint and target any German radio transmission within minutes. German codes were deciphered, frequencies were monitored, and troop movements were tracked through analysis of radio traffic. The final collapse occurred in late 1944 and early 1945 as Germany's industrial infrastructure disintegrated under Allied aerial assaults. Factories producing radio equipment became prime targets. Telefunken's Berlin facilities were annihilated in November of 1944. Lorentz's production plants in Stuttgart endured repeated bombings. The Crystal manufacturing facility in Sudetenland fell to Soviet forces in January of 1945. By March of 1945, German radio production had virtually ceased. Existing equipment continued to operate, maintained by increasingly desperate field technicians who scavenged parts from damaged units and improvised repairs with whatever materials they could procure. Replacement radios were simply non-existent. When a headquarters radio failed, commanders lost contact with their formations. When tank radios broke down, armored units became isolated groups of vehicles incapable of coordinated action. The Americans, meanwhile, continued to enhance their equipment even as victory loomed. New radios introduced in early 1945 offered augmented range, additional channels, and improved dependability. Production persisted at full capacity, not out of necessity for more radios, but because the industrial apparatus could not be readily deactivated. By May of 1945, American depots were overflowing with surplus radio equipment that would never see combat. The war concluded on May 8, 1945. Germany unconditionally surrendered to Allied forces. Among the items cataloged by occupation authorities were the technical intelligence reports from Tunisia, Sicily, and Italy. These documents, classified most secret by German authorities and concealed in salt mines and underground archives, provided Allied investigators with an unparalleled perspective on their own equipment. American technical teams scrutinizing German facilities in the summer of 1945 expressed surprise at the thoroughness with which the Germans had examined captured American radios. The reports were accurate, detailed, and professionally executed. They correctly identified American technical advantages and honestly appraised Germany's inability to rival American capabilities. One report, penned by Oberingenieur Klaus Hermann in April of 1945, as Soviet forces advanced on Berlin, served as his final testament to the technical conflict. He wrote that Germany's defeat was predetermined from the moment German engineers first opened a captured American radio in Tunisia. The frequency crystals, automatic circuits, and modular design revealed an industrial philosophy that Germany could never emulate. The Americans had industrialized warfare itself, applying mass production techniques to every facet of military hardware. Hermann concluded that future conflicts would be won not by the side possessing superior soldiers or tactics, but by the side with the greater industrial capacity to produce high-technology equipment in overwhelming quantities. Germany possessed excellent soldiers, competent generals, and adequate tactics. What Germany lacked was an industrial base capable of matching American production. This deficiency was most strikingly evident in something as seemingly simple as a radio crystal, precisely ground to exacting tolerances by teenage girls in factories that churned out millions of units annually, while German laboratories struggled to produce thousands. The post-war fate of the German engineers who analyzed captured American equipment mirrored the realities of the new global order. Klaus Hermann was recruited by American authorities in 1946 and spent 2 years documenting German radio technology for United States intelligence. He subsequently worked as a consultant for American electronics firms, assisting them in understanding and enhancing German innovations that warranted preservation. Many of his colleagues followed similar trajectories. The intellectual migration from Germany to America, formalized through Operation Paperclip and comparable initiatives, transferred thousands of German scientists and engineers to the United States. They brought with them knowledge of German technology, but more importantly, they assimilated American industrial methodologies, mass production techniques, and the organizational philosophy that had ensured American victory. In 1952, Hermann published a technical paper in the Proceedings of the Institute of Radio Engineers titled Comparative Analysis of German and American Military Radio Design Philosophy, 1939 to 1945. The paper, drawing upon his wartime experience analyzing captured American equipment, articulated in academic language what he had previously reported to the Wehrmacht High Command nearly a decade earlier. He wrote that American radio design prioritized ease of manufacture, simplicity of operation, and reliability under all conditions over technical sophistication or component efficiency. German design pursued technical excellence, theoretical perfection, and component economy, presuming that skilled operators would compensate for equipment limitations. One philosophy scaled effectively to millions of units and global deployment. The other did not. The paper became compulsory reading in engineering schools and military academies. It influenced a generation of American engineers who designed equipment for the Cold War, the space race, and the computer revolution. The insights gained from German engineers analyzing American equipment shaped American technological dominance for decades. By the 1980s, many surviving German engineers who had been involved in technical intelligence during World War II reconvened for reunions and historical conferences. They shared recollections, exchanged information, and reflected on their experiences. Klaus Hermann, then in his 70s, delivered presentations on his work examining captured American radios in Tunisia and Italy. At a conference in Munich in 1986, he displayed photographs of the initial SCR-508 unit his team had examined in February of 1943. The images depicted young German engineers poring over the opened radio chassis, measuring circuits, documenting components, and striving to comprehend their findings. Herman informed his audience that the moment they removed the first crystal holder and observed 10 precision oscillators integrated into a standard tank radio, he knew Germany had already forfeited the war. The frequency crystal, a small quartz wafer meticulously ground to precise dimensions, represented the convergence of physics, engineering, and industrial organization. Its principle was not complex. Any competent laboratory could produce one. However, manufacturing millions to a uniform quality standard with perfect interchangeability at a cost low enough for incorporation into every military radio necessitated an industrial infrastructure that Germany simply did not possess. That infrastructure, established in America between 1941 and 1945, did not dissipate with the war's conclusion. It expanded and evolved, yielding transistors, integrated circuits, microprocessors, and ultimately the computers and communication systems that define the modern era. The same companies that had mass-produced radio crystals for Sherman tanks later manufactured semiconductors for space missions, microchips for personal computers, and the components that enabled global telecommunications. The lessons learned from German engineers examining American equipment in Tunisia became integral to the foundation of modern technology. Design for manufacturability, standardized components, simplified operator training, integrated testing within the production process, scaled production to meet demand. These principles, evident in every aspect of American radio equipment during World War II, became the standard methodology for all high-technology industries. In 1995, on the 50th anniversary of the war's end, the Smithsonian Institution inaugurated an exhibit titled Communications and Victory: The Radio War, 1939 to 1945. Among the displays was an SCR-508 tank radio, its serial number matching the unit examined by Oberingenieur Herman in Tunisia in February of 1943. The radio had been recovered from German archives and returned to the United States as part of a cultural exchange program. Alongside the radio, the exhibit featured excerpts from German technical intelligence reports translated into English, documenting the examination process and findings. Visitors could read Herman's observations on crystal quality, circuit design, and manufacturing sophistication. They could view photographs of German engineers measuring components, testing circuits, and recording data. The exhibit clearly demonstrated that German technical experts recognized American superiority, reported it accurately to their superiors, and understood its implications. The exhibit also showcased German radio equipment for comparative purposes. A Fuji 5 tank radio was placed beside the American SCR-508, facilitating direct visual comparison. The German radio was larger, heavier, more complex to operate, and inferior in every measurable aspect. It represented excellent engineering constrained by limited industrial capacity. The American radio embodied adequate engineering, amplified by virtually unlimited industrial resources. The curator's notes explained that the exhibit's purpose was not to laud American technology or disparage German equipment. Both sides had competent engineers who designed effective equipment within their respective constraints. The difference lay not in intellect, training, or theoretical knowledge, but in industrial philosophy and manufacturing capacity. Americans constructed systems that functioned reliably when operated by minimally trained personnel. Germans built systems that performed brilliantly when operated by highly skilled experts. One approach scaled to global warfare, the other did not. The concluding display in the exhibit was a small glass case containing a single radio crystal recovered from the SCR-508 examined in Tunisia. The crystal, no larger than a postage stamp, consisted of precisely cut quartz housed in a hermetically sealed metal casing. The accompanying label explained that this crystal, one of 10 installed in a standard American tank radio, represented approximately 40 hours of German skilled labor to replicate. The Americans had produced over 100 million such crystals during the war, an output that would have required every German radio technician to labor for 500 years. The exhibit attracted over 200,000 visitors during its year-long run. Many were veterans who had operated the radio equipment on display. Some were engineers interested in technological history. A few were historians studying the industrial dimensions of warfare. All departed with a more profound understanding of how industrial capacity dictates military outcomes. Klaus Hermann passed away in 1997 at the age of 84. His obituary in the Institute of Electrical and Electronics Engineers Spectrum magazine highlighted his contributions to radio technology, his work in technical intelligence during World War II, and his post-war career assisting American companies in understanding German innovations. The death notice also emphasized his lifelong conviction that Germany's downfall was not sealed on the front lines, but rather within its manufacturing facilities, not by the bravery of soldiers, but by the tireless efforts of production staff, and not due to tactical blunders, but because of limitations in its industrial might. His extensive research, entrusted to the Deutsches Museum in Munich, comprised over 2,000 pages of technical analyses, schematic drawings, detailed specifications for components, and strategic evaluations penned between 1943 and 1945. These records afforded historians a granular understanding of how German technical experts perceived American gear and what intelligence they relayed to the Wehrmacht High Command. Arguably, the most affecting piece within this collection was a personal dispatch from Hermann to his wife in April of 1945, coinciding with the fall of Berlin to Soviet forces. He had dispatched his family to relatives in Bavaria several months prior, remaining in the capital to finalize crucial technical assessments until he received orders to evacuate. In his letter, he stated his intention to obliterate all sensitive documents and equipment to prevent their seizure. He reflected on the 3 years dedicated to scrutinizing American apparatus, from the initial SCR-508 in Tunisia to the most recent radar systems captured during the Battle of the Bulge. Each instance, he noted, corroborated a singular conclusion. America not only possessed superior equipment, but also an entirely distinct methodology for waging war. They had industrialized every facet, from radio crystals to entire military formations, applying the identical mass production ethos that fueled the creation of automobiles and refrigerators. Germany, Hermann lamented, had attempted to wage an industrial conflict using artisanal techniques. It was not that German ingenuity was deficient. In numerous domains, Germany's theoretical knowledge surpassed that of America. However, theory alone does not secure victory in war. It is production capacity that does. The nation capable of fabricating more tanks, more aircraft, more radios, and an abundance of everything else will inevitably vanquish any adversary, regardless of their skill or valor. He concluded his correspondence with a forecast. The next global conflict, should it arise, would be even more heavily industrialized than the last. Supremacy would belong to the nation possessing the most substantial manufacturing capability, the most advanced technological infrastructure, and the capacity to generate precision elements in limitless volumes. America had demonstrably showcased these capacities between 1941 and 1945. Any future adversary would need to match or surpass America's industrial prowess, a feat Hermann considered unattainable for any single country. History validated his foresight. The Cold War that ensued after the Second World War evolved into a contest of industrial capacity, technological advancement, and manufacturing might. The Soviet Union, despite its vast territorial resources and immense population, could not compete with American output in electronics, computer science, or industrial automation. The disparity that Herman had identified in radio crystals in 1943 expanded to encompass semiconductors, microprocessors, and integrated circuits. The narrative of German engineers examining captured American radio equipment ultimately narrates a tale of industrialized warfare and the manufacturing revolution that swept across America during the Second World War. It speaks to the metamorphosis of warfare from an endeavor primarily governed by tactics, troop preparedness, and courage to one dictated by industrial strength, technological sophistication, and manufacturing efficiency. The frequency crystals that so astonished Herman and his associates were not some miraculous anomaly. They were the product of precision engineering, certainly, but more significantly, they were precision engineering scaled for mass production. American industry had mastered the art of producing millions of identical units, a feat unprecedented in scale. This proficiency, honed for radio crystals, extended to every category of military hardware and eventually permeated every consumer product manufactured in America. The lessons imparted to German engineers through their examination of American equipment in Tunisia, Sicily, and Italy were harsh but unambiguous. Superior individual materiel is meaningless if it cannot be manufactured in vast quantities. Sophisticated technology is futile if operators cannot utilize it with reliability. Theoretical brilliance is worthless if manufacturing cannot achieve it consistently. Industrial capacity, when properly organized and directed, triumphs over all else. These lessons, acquired at the price of Germany's defeat, formed the bedrock of modern manufacturing philosophy. Design for efficient production, embed quality during creation, provide effective user training, ensure robust equipment support, and scale operations to meet demand. The principles evident in American radio equipment during the Second World War now guide global manufacturing across all sectors. Ultimately, the chronicle that commenced with Obering engineer Klaus Hermann opening a captured radio set in Tunisia in February of 1943 concluded with a complete overhaul in how nations prepare for and engage in hostilities. The radio crystal, that minuscule piece of precisely engineered quartz, emerged as an emblem of the Industrial Revolution in military affairs. It signified the moment when victory ceased to be primarily determined by battlefield prowess and began to be dictated by factory output. The German engineers who examined American materiel understood this transformation as it unfolded. Their reports documented not merely technical specifications, but the demise of one form of combat and the inception of another. They bore witness to, analyzed, and reported on the future of conflict. The fact that their warnings went unheeded in Berlin did not detract from the accuracy of their analyses. Today, the principles they identified, mass production of precision components, industrial automation, standardization for interchangeability, and design for manufacturability, are foundational to every high-technology industry. A direct lineage connects radio crystals ground in American factories in 1943 to microprocessors produced in Asian foundries in the 21st century. The industrial philosophy remains constant, only the magnitude has shifted. The German technicians who tested captured American radio apparatus in 1943 were not merely scrutinizing communication devices. They were observing the future of warfare, technology, and industrial organization. Their comprehensive reports, classified and archived during the conflict, eventually became historical documents that elucidated not only Germany's defeat, but also how industrial capacity dictates the outcome of contemporary conflicts. Their conclusion, articulated in technical parlance but unmistakably clear in its import, was that Germany had challenged the world's preeminent industrial power with insufficient manufacturing capacity. The radio crystal, a precisely cut quartz oscillator manufactured by young American women in quantities Germany could never replicate, told the entire story. Industrial warfare necessitates industrial capacity. Without it, no amount of tactical acumen, technological innovation, or individual bravery can secure victory. That lesson, learned from American radio equipment housed in subterranean laboratories across occupied Europe, retains its relevance today. In an era of microelectronics, satellite communications, and computer-controlled warfare, the fundamental truth endures. The side possessing greater industrial capacity to produce high-technology equipment in overwhelming numbers will ultimately prevail. The Americans unequivocally demonstrated this principle between 1941 and 1945. The world has been adapting to its consequences ever since.